Hello and welcome to the introductory video of the introduction to the first course on quantum mechanics. Now, in this lecture series, we are going to undertake an immense task of studying quantum field theory as our first course. Now, the aim of this lecture series is twofold. One is to understand the fundamentals of quantum field theory very clearly. Second is for you to prepare for the advanced text like Peskin and Schroeder with confidence. Now, Peskin and Schroeder is considered to be the Bible of quantum field theory. Now, it's a massive 900-page book. However, in order to tackle that, we need some of the introductory gap. So, this video lecture is what makes sure that you understand that, and it acts as a bridge between you to tackle the advanced text with confidence. Now, let's dive into the course structure. Now, the course structure is divided into 5 modules. First module is the relativistic dynamics. In Unit 1, we'll study why do we need QFT. That's one of the important questions that we need to ask ourselves no matter what field of physics or science by extension that we are studying. Why do we need this subject? So we'll look into that. Then we'll see a brief introductory session on quantum mechanics and special theory of relativity. Although this are meant to be a refresher, I assume that you have enough knowledge of quantum mechanics and special theory of relativity. I'll talk about the prerequisites of this course later part of the video. So let's focus on the course structure for now. Now, then we'll move on to the natural units. Natural units are one of the most important unit that we need to understand in order to understand the whole quantum field theory. Then we'll move on to slowly the classical field theory. Now, the classical field theory again is, I won't assume that you need classical field theory. However, since it's a first course, I won't assume any prerequisites on classical field theory, although I might need your kind attention in this. So we are going to cover the classical mechanics, which I assume you know. It's a quick recap. Then we'll move on to the Euler-Lagrange equation in the field theory. It's somewhat different in the field formulation. Then we also slightly polish the Hamiltonian formulation and the symmetry and Noether's theorem. It's going to be very important. Now, in this unit 2, classical field theory, we are going to have a very brief outlook of classical field theory. By no means this is a complete review on the subject. If you are interested, just ping me in the comment. I'll suggest you some of the books or lecture series that are available on YouTube, or you can just go for the books as well. Now the third unit is the quantization of field. Now we'll slowly move on to the quantization of field. We'll see how the real fields are quantized, how the complex scalar fields are quantized, and then we'll move on to the quantization of Dirac field. Now quantization of Dirac field is one of the most important unit that we need to cover, and then we'll move on to the module 2. Now module 2 is interacting fields and the Feynman diagrams. You all know what Feynman diagram is. I mean, if you don't know, you might have heard about the Feynman at least. Now the S-metric expansion. In this unit, we are going to cover the interaction representation, then we'll derive the evolution operator, and then we'll define the S-metric expansion through this evolution operator. Then we'll move on to the Fick's theorem. Now Fick's theorem is very important as we move along the quantum field theory. Now the second is of course our favorite Feynman diagrams. So Feynman diagrams is quite vast. So I handpick some of the topics that might be important and will give you some of the most intriguing ideas of how the Feynman diagrams are drawn for particular interactions. Now Yukawa interaction, which is also a decay of a scalar interaction. This is going to be our primary centered lecture series. The Feynman diagrams are focused on this particular interactions, and we'll see what happens if we normalize the state. There arises some kind of problem that we need to tackle, and we'll also fix that in this unit 2 Feynman diagrams, and we'll see the Feynman rules and Feynman aptitude, which are not S-matrix elements. Now then we move on to the unit 3, the cross sections and decay rates. Now although cross section is hard for me to cover given this is the first course of quantum field theory, so we'll stick on to the decay rates. So decay rates and decay of a scalar into a fermion antifermion pair is going to serve as a helpful example in this section. And scattering of cross section, very briefly. I don't know, I might not cover it. If time permits, I might do it, but mostly it's a no from my side. Now, module 3 is quantum electrodynamics. Now, you might be thinking quantum electrodynamics is a course itself. Now, how are you going to condense it in just one module? Yes, that was a challenge. That is the challenge. However, we are going to see a very brief overview. Now, so this, so as I said earlier, this is going to serve as a bridge course. So whenever we are tackling some of the advanced textures on quantum electrodynamics, this is sure going to help you. So in this unit one, we'll see what happens for the quantization of electrodynamics. There arises some problem while quantizing the classical theory. So what are the problems that arises? Then we'll move on to the Feynman rules for the photons. Although I won't go into the details, I'll just state these are the rules. Then we can move ahead to some of the most interesting phenomena rather than wasting time on studying the Feynman rules or deriving Feynman rules itself. Now, then Unit 2 is the core of this module, which is the quantum electrodynamics. We see what is the local gauge invariance. So, an interaction Hamiltonian, we need to know how to write an interaction Hamiltonian. Then we'll see some of the most simplest examples. So, that's called the tree level process. So, when we draw Feynman diagram, we see what are the tree level processes and what are the other higher order processes, but we'll mostly stick on to the tree level processes as this is the first course on quantum field theory. Now, unit 2 core is electron-electron scattering. It's very important for us to understand how the electron-electron scattering happens, and this is one of the most beautiful example of quantum electrodynamics. Now, the fourth module is the most difficult one. It's called the renormalization. You pick any syllabus of any university, you will not find renormalization as one of the modules in the QFT1. However, as I said earlier, this is a bridge course. We are not going to study many things. We are just going to briefly overview. Although I will not shine on mathematics, but this is the topic that you need to be very careful and very attentive. Module 4 is the renormalization. We'll see what is the superficial degree of divergence. First, we need to understand what the renormalization is. So we'll see that as well. So what are the outline of renormalization? What are the different types of regularization that is possible? What is regularization? Of course, we'll see. Then we look on to the vacuum polarization diagram as our primary example. So fifth is the counterterms and the Lagrangian and the Watt-Takahashi identity. So the Watt-Takahashi identity serves as some kind of connection between all this. There is something called vacuum polarization diagram, self-energy diagram, and so we'll see. So now, my professor always keeps saying, if a theory is not observable, then we can throw that theory into the garbage. Now, however, renormalization is not one of them. Observable effects of renormalization has been considered, and we will see what are the different types of observation that have been observed by LHC or the ongoing experiment of the last decade or even the last century. Now, Module 5 will slightly going into the direction of the standard model of particle physics. So now we are proceeding from QFT to the standard model of particle physics. So we won't go into the detail, of course, because particle physics is a course itself. So in this module 5, what we are going to do is we are going to briefly see some of the phenomena that you might have heard, such as the Higgs mechanism. You might have heard this is the Nobel Prize winning mechanism. So we might see this as well. Then we'll see the standard electroweak theory. It is unification of electric and electroweak. Yeah, so we'll see that as well. So this is a brief outlook, and this is a brief module. That this is the core structure that we will follow strictly. We will not deviate from this. So if you have any problem or you want to know anything about this, you can always contact me in this particular email. Or if you want to contact me on a personal email, the email is in the description. You can check it out. Now, what are the prerequisites for this course? Now, I assume that you know quantum mechanics very well. At least, I assume graduate level. Now, although people say Griffiths is kind of sufficient, I don't agree. I think Zetley's quantum mechanics is quite good, or Sakurai is one of the best books that's available on quantum mechanics. So, actually, what I'm saying is we need the Dirac bracket notation formulation. So I hope you master it quite well in order to tackle this, because this is going to serve at each and every step of quantum field theory. Now, second is special theory of relativity. Again, many standard books are available. You can check it out. I think most of the undergraduate covers special theory of relativity and mathematical physics. I have to be a little skeptical here. What in mathematical physics? I mean, I can't say everything, but if you are searching for good books, then I think Afghan is a very good book. Or you can also check some of the other courses that's freely available on YouTube. If you're interested, just ping me in the comment. I'll just share the link with you. Okay, so these are the three prerequisites, I assume. Now, in mathematical physics, I don't know, linear algebra is, of course, a must. LA, linear algebra. Then I also assume some of the you're very much comfortable with integration and differentiation. Um, then you're also quite comfortable with the complex analysis. We will be using some of the part of the complex analysis rather than proving the complex analysis. No, we are going to use it, of course, because the iota comes in into the factor, right? We know that from quantum mechanics. So we need the complex analysis. And I think, yeah, quantum mechanics is very much the need, and special theory of relativity. Now, why we need special theory of relativity, again, you'll understand in the next video. So, yeah, so that's the prerequisites for this course. So, what are the books that I want to follow? So, for this lecture series, the primary reference is going to be this book. Now, this is the first book on quantum field theory. Now, this is a beautiful book, and this is the book that I followed during my electives last semester. So this is a quite good book. So other reference that if you are interested that I followed was Ashok Das. Now these two books can go hand in hand. They both have similar approaches. Now Ashok Das has also other book which is canonical, path integrals method. So I think this is the book that I used, and this is the book that I recommend as well. So, but for our course, this is going to be our primary reference. Okay, so I won't bore you much about this course detail. You can check it out in my website, which is freely available. If you're interested in the course structure, you can download it from my website. The link is in the description. And thank you so much, and I'll see you back in